the image, then the GCM should have large values along the diagonal corresponding to the gray levels in the texture elements. So the chi-square statistic was computed, this PL1, L2, and this marginal and normalized by the marginals. And the measure was normalized by dividing by L. It is expected to possess a high value for periodic texture under these conditions. And then they proposed a measure of agreement, kappa, as P0 or P0 minus PC or 1 minus PC, P0 being the sum of PLL over all L, and PC being the marginal probabilities combined this way. And they found that, or showed that, this kappa has maximal value of unity when the GCM is a diagonal matrix, which indicates perfect agreement of all periodic texture. So they showed that texture analysis can be performed with appropriate D and theta to detect periodic texture. Chan and others who have worked on who have published many papers on mammography, they found correlation, difference, entropy, and entropy to perform better than the other features. They tried many of these features. And we have seen many other papers where not all the 14 texture parameters have been found to be useful in practical applications. So 3 to 5 of them have been found to be useful in practical applications, and many studies use only the first 5 or so. Sahaina and others developed what they call a rubber band straightening transform to map ribbons around breast masses. Okay, this is beginning now, into rectangular arrays, and then computed Harlick's measures of texture. The point or the problem or the issue is these co-occurrences are defined on a rectangular grid or on a rectangular image. You need to look for neighbors and scan in a certain way. But if you have some irregular shaped objects like a calcifications are too small, let's say tumors, then it'll be, many of the pixels may not have neighbors for the d theta parameter specified. And then the counts for such parameter values in the GCM may not be meaningful. So it's been shown to be advantageous to convert the region for which you are computing texture when it is not a rectangle into a rectangle by mapping in some way, geometric transformation. And also in the case of breast masses and tumors, what is inside the core of the tumor quite often is not important. The texture inside may not be important, but what is around the ribbon or the periphery of the tumor is more important. That is, how the mass is interacting with the surrounding tissue. In the case of a benign mass, there is not much interaction. There is a sharp edge and the mass is sort of contained. In the case of a malignant tumor, it is spreading, so there is some interaction and the surrounding tissues are being disturbed and modified by the malignant or cancerous tumor. So then it is that periphery that is important around the tumor and not what is at the core of the tumor. So Sahaina said we will take that, but it is a thin ribbon of some odd shape and size. The thickness is fixed, but the shape could be something different for each image. But how do you compute the texture parameters? They said, okay, we will stretch it into a rectangular ribbon. So they called it rubber band, like a rubber band, and make it rectangular. My PhD student, Naga Mudigunda, he took a different approach. He used adaptive ribbons of pixels extracted around mammographic masses and tumors and used the features to distinguish malignant tumors from benign masses. So we will see some of that later on in the application part. There's a paper by Loss who came up with a different notion for texture known as texture energy. It is not based on counting pixels, but instead computing a measure of energy after applying certain filters to the given image. So he said the texture energy could be computed by taking the energy of a filtered version of the given image, The filters determine what kind of energy you're computing or what kind of pattern is being represented by that texture energy. The texture energy features represent the amounts of variation in a sliding window, so you're computing energy in a small window and making another image and then using that as a feature. The filters are specified as separable 1D arrays for convolution, and then combining the 1D arrays you get 2D operators. So the 1D operators were defined in this manner, 1 to 1. Now when you take one of these and multiply with the transpose of the same or another, then you get 3 by 3 matrices. So 1 by 3 times 3, or 3 by 1 times 1 by 3 will get 3 by 3. So 3 by 3 masks were generated by multiplying the transposes of each of these three operators with their direct versions. So L3T, L3 transpose E3 gives one of the 3 by 3 Sobel masks, like a differentiation operator. And then operators of 5 pixel length were generated by convolving L3, E3, S3 in various combinations. When you convolve a string with 3 values with another string with 3 values, you get 3 plus 3 minus 1, 5. And then those were combined in this manner, taking the transpose of one and another, and L5, T, E5, and so on. I don't have all of those numbers here, it's not important, but the basic operators are these, and they were extended to have the length of 5, and then they were combined the transpose of one with another to make 5 by 5 operators. And there are gradients and edge and spot detectors of various kinds. So when you convolve the image with these, you are detecting such patterns. And the image will have positive and negative values for these operators. You square, and then you take the energy of that. So these are the operators of length 5. So this is convolution of one with another. So these were called local average, edges, spots, ripples, and waves. Detection of those patterns. So depending on what kind of patterns you have in the image, one of these, or the corresponding one of these, will give you a high energy in the output. And then they made 5 by 5 operators further, taking L5 transpose L5 or L5 transpose E5 and so on. So this is the familiar Lena image, but she is not popular anymore. Journals are now telling not to use this, so I have removed her from the book. This was, I think I mentioned that, in the 70s and 80s, not many labs had image digitization equipment. And there was an image processing lab at one of the universities in the US. They made these available on some sort of a website, or there were no websites then. Some downloading FTP facility. So researchers got those and wrote papers. We also did the same. But now journals are telling, an interview was done with her, and she said she was happy that so many researchers were using her pictures. Nobody shows the rest of the picture. So this is the original picture. This is after the smoothing operator, ELF. No, this is with L5, L5, and then it is going this way, sorry. B is L5, L5. No, A is L5, L5, B is E5, E5, C is W5, W5, and these are by taking the sum of the absolute values of these results in a 9 by 9 moving window. So you have to average this. Here you have positive and negative values. You can take the sum or square, and these represent the energy, texture energy as called by laws. And these are mapped for display. So it's not exactly the values. For example, the full range was minus 1338 to 1184, mapped to 0 to 255. So mapping will sometimes shrink the effect of the display. Fractals can also represent texture. There are many methods of generation of fractals. The most common definition is a pattern composed of repeated occurrences of a basic unit at multiple scales and in a certain order of generation or placement. This is known as self-similarity. The same pattern or motif appears, but at multiple scales and in a certain ordered pattern. It is also seen as a nested recurrence of the same motif at smaller and smaller scales. Nesting is when one goes inside another, but sometimes it might not be going inside, but they are placed in some order. In nature, we find many fractals, and Mandelbrot said mountains are not triangles and clouds are not spheres. They are modulated by repeated occurrence of multiple scales. So a mountain, if you draw like this, that's one basic mountain. But then if you put more and more triangles and keep subdividing those triangles into smaller and smaller triangles, then you get a real mountain. The same with clouds. You take a circle and make it macrolobulated, take each lobule and lobulate it again in 3D, then you get a cloud. So that kind of a pattern is also a fractal. The motif is like a triangle or a sphere, or some kind of a pyramid and a sphere in 3D. The self-replicating patterns of the leaf structures of ferns, I'll show you a picture. The ramifications of the bronchial tree in the lung, I showed a CT image of a part of a lung with those branching patterns. That is also a fractal. You start with one tube and it branches, and take each branch and keep doing the same thing. They become smaller and smaller, but that is a fractal. And that happens in the arteries of the heart also. So that's a fern leaf from our garden. So the same pattern occurs. The whole thing looks like that. And then you look at one of these, it looks, if you were to take this and expand, it will look like the whole thing. And take that and expand, it will look like that, but there is a limit. There are only 3 scales. Beyond that, if you take this, there is nothing more. So it's a physical object. So the number of levels of this is limited. Whereas in computer-generated fractals, you can keep zooming and you can keep generating more and more. But that is simply replicating the pattern and recreating it. It's not there in the original image. If you zoom, just take a static image and zoom, you'll start seeing pixels. But what is displayed in computer animated displays of fractals, the same pattern keeps appearing, looks like infinity. But had it been a static one print and you zoom in to a factor of 4 or 5, that pattern doesn't exist anymore. So if your image is of a fixed number of pixels, yes, the same pattern occurs at smaller and smaller size or scale, but if you zoom in at some point, that pattern is lost. And the same in true physical entities also. You need some material to make this, and the material takes up some space and some material, space. So you cannot have this pattern to infinite levels of resolution. But that is a fractal. So fractal, in some cases you can come up with a dimension and say there is a certain number of stages of this happening. In some cases you cannot put a specific number. The fractal nature is related to complexity, and that is expressed in terms of a fractal dimension. If you were to take a straight line, it is a 1D function, but if you take a function of time that is varying, or some one-dimensional function with variation, that is not one-dimensional, it is between 1 and 2 dimensions. In order to plot it, I need a 2D surface, the board, to plot that. But it's a 1D function of one variable, but it's not a straight line. So the Euclidean dimension of a straight line is 1, but that of a curve or some signal like a speech signal or ECG is not 1. It's not 2. It's 1 point something. Similarly, an image, it's not flat and smooth like this, so it's not just a flat two-dimensional surface like the board, but it has some gray level variations which could be seen as variations in height. Then it is sort of between 2 and 3D. So the fractal dimension will be more than 2 but less than 3, and so on. So this is the notion of fractal dimension. So one of the common examples given is that of measuring the length of a coastal line. They always go coastal line of England. I don't know why it cannot be Mangalore or some other place. Any coastal line will have these irregularities. So if you go and walk on the beach, how do you measure the distance between 2 points? So if you just go put a straight line, straight ribbon or a ruler and measure, then you get 1, but you are missing all those other details. If you start measuring all the details, it depends on the size of your ruler as to how big your ruler is. I don't have a ruler here. There is something. You measure this 1, 2, 3, 4, and so on. Any detail that is smaller than this will be missed, skipped. So you take an even smaller ruler, 1 millimeter, and start measuring 1 millimeter at a time. Then the distance or the length of that coastal segment will be longer and longer and longer, with finer units of measurement or the scale of measurement. So if it is a straight line, then no matter what the size of the ruler is, you will get the same value always for a straight line. So that's another notion of a fractal, where the measure that you get depends on the scale of your measurement. So use of a larger ruler to measure the length of a coastline, minor details in the border having small scale variations will be lost, and a certain length is derived. If a smaller ruler were to be used, you get a larger length between the same two endpoints. So this relationship is expressed as L eta. Eta is the measuring unit, the size of your ruler. L eta is the length measured. DF is the fractal dimension, and L naught is some constant, the size of that ruler that you're measuring in millimeters or centimeters. So the fractal dimension comes up in this relationship. You take the log and you get this relationship. The log of the measured length is some constant plus the log of the scale with 1 minus df as the slope of that relationship, and df is the fractal dimension. For a straight line, df is equal to 1. So you get one quantity. So this is known as the ruler method or the caliper method to estimate the fractal dimension of a curve. You could view fractal dimension as a property of that curve as to how it fills space. There is a certain space and you could fill it. If you just have a straight line, it only takes up that much space over your grid. But if I draw some other pattern, it is taking more space. But it is still a line. The fractal dimension of a straight line is unity. That of a circle or a 2D perfectly planar sheet light object is 2. That of a sphere is 3. But as the irregularity or complexity of the pattern increases, the fractal dimension increases up to its own Euclidean dimension plus 1. So there are space filling curves. It's a one-dimensional curve, but it will fill a 2D space, like the piano Hilbert curves. The fractal dimension of a jagged, rugged, convolution here is not mathematical convolution, but something that is wrapping on itself. Kinky or crinkly curve will be greater than unity and reaches the value of 2 or approximates or move towards the value of 2 as its complexity increases. And in terms of images, the fractal dimension of a rough 2D surface or image will be greater than 2 and goes towards 3. So in that sense, It's a measure of roughness. So you need to recognize what you are representing by this parameter. There are a few more definitions. There is one called relative dispersion. RD of eta is the ratio of the standard deviation to the mean using varying bin size. So RD eta is the reference, RD eta naught is a reference value for the bin size, and eta over eta naught to the power of h minus 1, where this h is known as the Hurst coefficient. And the fractal dimension df is given by the Euclidean dimension de plus 1 minus h. So de is 1 for 1D signals, 2 for 2D images, and so on. So the value of h and from that the fractal dimension may be estimated by measuring the slope of the straight line approximating to the relationship of log of what you're measuring to log of that, the scale of measurement. And the same applies to the ruler method and a few other methods. There is another model known as the fractional Brownian motion. So here, the expectation value of the difference, f eta plus delta eta, some displacement minus f eta. It could be a function of time, space, whatever. So the displacement is delta n, delta eta here. And the expectation of the absolute value of that is proportional to delta eta, that displacement, to the power of h, the Hurst coefficient. So again, you take the plot of the average difference as above versus delta eta on a log-log scale and fit a straight line and use that slope to estimate the fractal dimension or the Hurst coefficient, and the two are interrelated. So there have been many applications in medical imaging and image processing. Chen applied fractal analysis for the enhancement and classification of ultrasonographic images of the liver, and there are many. Benign masses have been modeled as smooth homogeneous texture, malignant as rough and heterogeneous, and they have higher fractal dimensions. But the difference is not that much. They have to be between 2 and 3. So the difference is like 2.4 to 2.5. Is that enough for pattern classification? It depends upon their variance also. The path spectral density of a fractional Brownian motion signal, phi of omega, taking it, for example, to be a 1D signal of time, for example, is 1 over omega to the power of 2h plus 1. The derivative of a signal generated by fractional Brownian motion is known as a fractional Gaussian noise signal, and the exponent in the power law relationship is this, for that is 2h minus 1. But here, in the path spectral density, it is 2h plus 1. So this is known as the power law. So how do you analyze texture using this? Based upon fractional Brownian motion model, this intensity difference IDK was defined, where you are taking FMN is the image, FMN plus K, some displacement, and sum on that, sum on M, and some N going N minus K plus 1, and plus in the other dimension, M plus Kn, for K, as an argument of K. So you compute this for different K, and a slope of this log IDK versus log K was used. And to that you fit a straight line, get the slope, get H, and from that the fractal dimension. And they gave various accuracies in the classification of ultrasonographic images of the liver. There is another. Bing came up with this method of surface area measure, where it's also known as the blanket method. Suppose you have this plane surface of the table and you want to cover it. You need a sheet of that area. But suppose you have all these objects and you want to cover all of them, you need a larger sheet to wrap around all of these. So if this area has lots of ups and downs and pillars and objects of various heights, then you need more and more of this blanket or sheet to cover all parts, including all these exposed parts. So that is known as the blanket method for that reason. So a flat picture with no variation requires a minimum area of the blanket to cover, and then more variations in texture or height of the pixels means larger blanket. So that is what is characterized here. Let me go to that. There's a picture there. So these are like buildings in downtown or somewhere. Let's say they are adjacent, and you want to cover not only the top areas but also these exposed areas in between the blocks. If all of the blocks have the same height, then you don't have these exposed areas in between them. Right? So the total surface area of the image is eta square plus eta, the difference between the adjacent pixel values. So if the differences are 0, then you just have eta square and as many blocks as you have. So again, you do the same thing. Take log of eta versus log eta and plot. And it is some curve at a straight line to approximate the slope. And in this case, you need to have some adjustments for the Euclidean dimension of the source. If it is an image, 2. If it is a one-dimensional function, 1. So the fractal dimension in this case is given as 2 minus the slope. A perfectly uniform image would demonstrate no change and have fractal dimension of 2 only. Images with rough texture would have increasing values of the fractal dimension, getting close to 3, but not possible to get to exactly 3. It has to be less than 3. So Yaffe et al. Obtained fractal dimension values in the range of 2.2 to 2.5 with 60 mammograms. So they showed, Bing and others showed that the fractal dimension was useful as a measure of increased fibroglandular density in the breast and related that to the risk of development of breast cancer. And fractal dimension was also found to complement histogram skewness that we mentioned earlier as an indicator of breast cancer risk. So the more variation of fibroglandular tissue of higher density, the larger this factor of fractal dimension. So variability of density and the presence of high density will increase fractal density in this blanket method. So there are some reviews there, we'll skip that. In the Fourier domain also, you can make some, you can derive some measures of texture. The Fourier spectrum of an image with random texture contains the spectral characteristics of the spot involved in the generation. We saw that the spectrum of the texture image looks like the spectrum of the spot. The random input has a flat spectrum and the effect of that is negligible. Thus, the important characteristics of the texture are readily available in the Fourier spectrum. Now, how do you characterize that is another. The Fourier spectrum of an image with periodic texture includes not only the characteristics of the spot, but also the effect of multiplication with the spectrum of the impulse field. So there are the high energy intensity points, as I'll show soon. I think the pictures will show this better. To see this effect better, in some cases, it may be useful to move to the polar coordinate system, FRT. R is square root of u square plus v square. T is tan inverse or arctan of v over u. And change the FUV from the Cartesian coordinates or rectangular coordinates to polar. Then integrate FRT along T and you get a function of radial frequency only. Integrate along R, you get a function of T only, T or theta. So here are some examples. The impulse field. I didn't put impulses at the end. The Fourier transform of that is another impulse field. The Fourier transform of an impulse train is an impulse train, periodic. You have seen that in sampling. But the spacing is the inverse. So this is a circle and its Fourier transform, the Bessel function, except for these artifacts. And a bunch of circles convolving this with that, we get this image, sort of periodic texture, except for the border and the spectrum. The spectrum is, we convolve here, so these are multiplied. When you multiply this with the impulse field you get spikes at those points. So you get this periodic concentration of energy, and the moment you see that, you know it is periodic texture. There is some periodicity of something. If you see such dots. Dots are concentrations of energy. If you convert this to the polar coordinate system, this is angle in degrees 0 to 180 and this is radius 0 to 128. You get this where you again see those points of concentrated energy. If you break that into the marginals, this is a function of radial frequency where the periodicity is clear. But this is a perfectly periodic signal. This is the function of angle and there is not much variation there because the spot is isotropic. But this shows periodicity. This is the Fourier transform of the fly's eye, and it has periodicity, so you see these spots. It's not as strong as here. You don't see all of this detail. This is a real image of the fly's eye with those patterns that I showed earlier. And converting to polar coordinates, I don't see much advantage. You see some spots here, but I think it's more evident here in this case. And getting the marginals did not really help in this case. This is of the snake skin, the cobra. You see some patterns here that are repeating. I don't see impulses as such, but there is a repeating pattern here. In polar coordinates we get that. In the marginals I was hoping to see more repetition, but it did not work in this case. One of my students tried homomorphic deconvolution of periodic patterns. I'm not sure how well this worked. We tried various patterns, but we got some limited success. Homomorphic deconvolution has been used in speech signal processing to extract one copy of the vocal tract response in the case of voice speech signals, where you have a repetition of a certain pattern, like the vowel A, and you can say this is the convolution with the impulse train, and the basic wavelet is this. So that is copied at every impulse. But there could be some natural variation from one copy of that to another. Homomorphic deconvolution has, can you see that? We should turn the lights on perhaps. In 2D, it's a bit more complicated. Even 1D deconvolution is not easy. There are many pre-processing steps required to achieve homomorphic deconvolution. I mentioned earlier, homomorphic filtering is based on converting the input operation that combines the input components into addition. Here, there is convolution. This is the basic pattern, and there are impulses in an impulse field, and at every location of the impulse, this is copied. This is a building. It's not precisely periodic. There are variations. We wanted to try if it works. It sort of works with some artifacts. So you take a log first take the Fourier transform that converts convolution to multiplication. Then you take the log, multiplication becomes addition. Then you apply a filter. A low-pass filter will give you one of this. A high-pass filter will give you the impulse strain. The impulse strain is difficult to extract even for a speech signal because of noise, and you try to do the inverse weighting after the weighting that is required to get the complex Kepstrom. The method has practical difficulties. We digitized a cloth with a piece of cloth with some repeated motif, this flower pattern, and we got that by deconvolution, extracting one motif out of a periodic presentation of that. Antonio also worked on auditory display of texture, but I won't go into that here. We'll skip that. I'll just show this image to explain one of our projects where we said, as I described earlier, when you are analyzing breast masses in mammograms, what is inside the mass perhaps is not as important as how the mass is interacting with the surrounding tissue and the contrast between those two regions. So for that, we took the contour drawn by the radiologist and dilated that in both sides, or just say dilated, such that we get a certain amount of the pixels inside the contour and outside the contour. So it's a ribbon molded to the shape of the mass. And then at every pixel along the boundary we drew normals, like computing acutance I described earlier. We drew normals and computed the acutance or edge sharpness measure. And using this ribbon, we computed the Harrelix texture measures. We didn't map this to any other shape. With high resolution, with the sampling distance being 50 micrometers, we get a good number of pixels to compute the gray level co-occurrence matrix. But still, the number of pixels is small compared to the entire image, or even this image, which is 1000 by 900 pixels. So the question arises as to whether we have adequate counts of pixels if the quantization is to a large number of bits. 8 bits should be okay, 10 bits will create difficulties with very sparse co-occurrence matrices. So we showed that reducing the number of bits doesn't help much. You may lose details, so 8 bits we remain there. And resolution of 200 micrometers was found to be good in the classification of masses. 50 micrometers and 100 micrometers yielded poorer results in classification using texture measures. But anyway, our initial work used this. That study was later on. So in the case of a malignant tumor, when we start doing this, this thickness was made adaptive to the size of the tumor. So in this case, not much was left out, but still, that illustrates the ribbon that is computed adaptively. And the normals. That's the original image. Mapping of ribbons into a rectangular band, as done by Sahaina and others, is shown here. Sahainer's paper shows this example where there is a tumor and that's the ribbon. They are taking pixels inside the boundary. We took inside and outside. And they do a geometric transformation of that band into a rectangular or a straight line, and that width is maintained the same. So you end up with a rectangle like this. The interesting thing that happens here is spicules going like that now are vertical lines. When the angle of this mapping matches a spicule, you get a straight line when you get that. So that observation helped us in designing a similar transformation in the detection of architectural distortion that I'll show you later on. In any case, the ribbon of some arbitrary shape is converted to a rectangular image, so computing the gray level co-occurrence matrix becomes easier, computationally simpler. But these are not the original pixel values, they are interpolated somehow. So that is all I have about texture analysis. If you refer to the, there is another PDF file called texture analysis. This is chapter 7. But the other file on texture analysis has some other examples, some more examples. You could refer to that if you wish. What else should I say? I think that's all I have for today. We said 4:30. Some of you were asking for 4 o'clock. It is 4:15. Compromise. Do you have any questions? We can have some discussion if you have any questions or comments before you leave. I don't want to start another topic for the last 15 minutes. So essentially there are multiple views of texture, and depending upon how you view texture, you may analyze using co-occurrences, frequency domain, representation, fractals, and so on. Fractals will come again later on when I will talk about architectural distortion and other applications. Yeah.
So it's more of an observation. I overheard Sir was saying something about a session on, I think, research problem identification or something like that.
Which one?
Research problem identification or something, because like we have some scholars. Okay, so like based on the fact that you have extensively worked on this area, so what's the scope for us? You know, like maybe for research, I mean, those going into PhD, okay, or those who want to do postdoc or something like that. Like how do we identify, you know, an area that interests us? Say I want to go to biomedical or something.
Yeah. That's a bit difficult. I would always say it should be context dependent and locally relevant. And you need collaborators. So the primary requirement is collaboration. So even for my PhD project in 1976, my professor introduced us to cardiologists. We went to the hospital, recorded signals, talked to them, and got some information from them as to how to classify heart sounds or ECG signals. We read textbooks, of course, but talking to the cardiologist helps. And then we have to get the data from patients too. And we need that collaboration. You must have the facility to go and get the data. Nowadays, you have databases available online. NIH, the National Institute of Health in the US, and many other countries require data obtained using their grants to be made public. Even China, they do that. If you get a grant from the government, they say you must put the data on a public database so everybody can use it. Fine. But the data must be annotated. I can't simply say, okay, take these 10,000 mammograms and do whatever. If nobody has marked as to what is it, you need the ground truth. You need a radiologist to mark the tumors or calcification or whatever. Without that, the data will be meaningless. The problem should be relevant to the local experts in medicine. That is, you should talk to them and ask them what are the issues that are relevant to them, where they would need your help as an engineer or computer scientist. If you say, I'll enhance your images, they say, no, I don't want enhancement. If you say, I can detect calcifications, they may say, no, I can see that. But there'll be something where they need help, and that is where you could contribute. It should also be fitting to the current trend in publishing. Of course, we want to publish. So you need to be in tune with the current trends in publication. Now, the current trend is deep learning. My colleagues have told me without deep learning, you cannot get a paper accepted. So DLC and AI, those things must be there. But previously that was not the case. We use different tools and we publish, but there must be some validation of the results with good data set and participation of the medical expert. You require the right tools and the background, and you have courses in DSP, image processing, pattern recognition, machine learning, or whatever you want to call it. All of those should be available, which I suppose are available everywhere. But the medical collaboration is something very important in our field, in the biomedical field, and the relevance of what you want to do to their practice. You asked about thermal imaging, and I have not encountered thermal imaging in Canada, but of the breast, but my colleagues are working on microwave imaging, and that seems to be gaining popularity. There are some issues there. The breast has to be immersed in oil for matching of the impedance, and that's not perhaps convenient. In mammography, the breast is compressed, and that causes pain, and that is not convenient either, but that's been accepted. So you want to change it, then you need to see what is acceptable and what is not acceptable according to your mode of or modality of imaging. So it is better to collaborate with medical experts where there is an established practice of acquiring images of a certain type and diagnosis, and then see how you can contribute to that. That's how we have developed all these projects. And in mammography, things developed in a certain sequence. We knew from textbooks in mammography that the calcifications, masses, asymmetry, architectural distortion, they're all signs or manifestations of breast cancer. But if you go back and see the sequence of papers developed and published, you will see calcifications first, easy thing done. And then people started looking into detection of masses. Initially 70%, 80% accuracy, and then it went up to 90, 95. And then they said, oh, we have forgotten asymmetry, but you have to analyze the left and right breasts, mammograms. So then that came up. Architectural distortion was ignored for a long time, and there were some very few papers, and then we started writing papers on that, and then there were more. So like this, a field develops in increments. Easy things are done first, and hard things are left out for others who pick them up later on. As I said, when new students come to me and ask for a project, I say, we should do this. They say, this is difficult. I said, yeah, all easy things have been done. Only difficult things are left for you. And they will get more and more difficult for the next generation as you finish all the current problems. It's not a direct answer. I can't say, do this. But it's an exploration, right? And perhaps your colleagues and for those of you who are students, your professors will have such connections. When I joined IISc in 1976, I didn't know anything about biomedical engineering. I knew we have a heart, but I didn't know about the ECG. I didn't even know what was hardware, software. I said, well, which one is which? And we had never seen a computer, right, until then. So we pick up things slowly. That's what the professors do. They teach us. Professor I.S.N. Murthy, my professor, he taught us courses on biocontrol, biomedical signal analysis, and 2 or 3 other courses, instrumentation. And we had courses on all these topics: digital image processing, pattern recognition, speech signal processing. So that way
we cannot leave mathematical aspect of that to solve that problem.
Cannot leave.
That means we should not, one cannot ignore or just...
Of course, yes, that's an important point. The radiologist will describe it in terms of visual attributes. Our colleague in radiology just said, well, spicules and there are these parts that are curving inward, and we had to think about how to characterize that, how to break that contour into parts, and how to characterize. It's very simple. Finally, that equation is very simple, but we are proud, well, it's my equation. And it worked to some extent. Concavity is such a simple concept, but it had not been addressed in previous publications. Why? Perhaps they did not talk to the radiologist. And we talked to our colleague in radiology many times on I wouldn't say every day, but we would have regular meetings. Our students would show their results, sit and discuss. It doesn't happen in one day. And then we need to convert that whatever description they give in words and pictures, they may draw something. And we said, I would tell my students, throw all of those pictures on the board or on the wall and let's stare at 100 of them and maybe some idea will come out. Arrange them and then you have to turn that into a mathematical algorithm that cannot be ignored, and how you implement in the program, that is the final issue. But you have to write an equation as to how you want to do that. So later on, I'll bring in the retinopathy of prematurity, and we came up with a new measure of tortuosity. Very simple equation, but there is no such method in the literature. And we need to write an equation and say this will capture what you want to analyze and give a number. I use the word encapsulation. That whatever that idea is, you have to turn that into an equation, and that equation should give you a number between 0 and 1 for that measure or attribute, so you can put that in a pattern classification algorithm. You don't want features that go minus million to plus million. You want 0 to 1 and all of them in the same range, so you can put them together. It'll be very hard if you have one feature that goes minus 10,000 to plus 10,000, another 0 to 1, another minus 500 to 60 or something. Pattern classification algorithms may have some difficulties. You can normalize them. But if you can bring them all to a certain range with a good mathematical concept or equation, then that helps. So one is talking to the medical specialists and listening and understanding how they're describing the problem. The other is how to write an equation to capture that. And then implement it as a program. That, I suppose, is not a big deal once you have a mathematical equation. Just a moment, please. We need silence here. Yeah.
Is there any connection between the modality and the textual analysis technique?
Between what?
The type of the medical image and the technique that we use to analyze the texture. Whether the technique changes depends upon the image.
No, texture is texture. So the same method should be able to characterize texture in different types of images. But when texture is not just random texture or one particular type of texture, if it is oriented, for example, and if it is intersecting patterns, like I'll show for architectural distortion, then you have to fine-tune. Any texture, any method to characterize random texture will not work there. You need the directional distribution to capture architectural distortion. Parallax measures will not do that because it's general statistical representation of texture. I'm not putting down parallax methods, but I'm saying that at first I said no, texture is texture, but there could be specific cases where you may need to design particular transformations. I'll show in architectural distortion again. We transformed the region of architectural distortion that was cut off, potential region, into polar coordinates and then computed loss texture features. If you compute loss texture features directly, you may not get the desired result because it looks for waves and spots. So waves and ripples rather. Waves and ripples don't appear in an architectural distortion pattern, but if you map Cartesian to polar, then as I showed in that rubber band, there are straight lines that sort of look like ripples. Then loss method will help. So some pre-processing steps may be required to apply the same techniques to get the desired result when you have some specific kind of pattern that may not fit the original formulation, but after some geometric transformation it may fit better. The basic idea remains the same. So after we finish the next chapter, which will be, I don't think I'll be able to finish it tomorrow. We will have a part of that, and Monday we will finish the next chapter, chapter 8 on oriented texture analysis. Again, I'll skip some parts and show only the most important parts. Then we will take up a few applications from our own research work. So then it'll be a little lighter, and you will see more illustrations of application of all of these concepts. More pictures. A few equations may appear, but they will all be related to what we have seen. So don't miss the application part later on. But of course, you need this also. All right, thank you.